Number 13 is a question on exam 1 material that talks about the stability of ions based on withdrawing groups and conjugation and donating groups. So let's look at each structure and first identify what kind of donating and withdrawing groups we have. NO2 is a very strong electron withdrawing group. And that's it for that special. OCH3 is a strong electron donating group. And another OCH3, so this also has a strong electron donating group. And now we have to figure out, well, how do donating and withdrawing groups affect a positive charge? Well, let's think about this for a second. A positive charge is an absence of electrons, right? You're missing electrons there. What withdrawing groups do is they pull electrons out of a system. So if you're missing electrons and you're having something suck out even more electrons from you, that's going to make that positive even more positive and even less stable. On the other hand, if you're empty and you have a donating group which loves to put electrons in, you're filling that empty space, so you're making that positive less strong and more stable. So the rule is electron donating groups stabilize positive charges, and electron withdrawing groups stabilize negative charges. Because if these were negative charges, that's an abundance of electrons, you want to pull them out, and that's what an electron withdrawing group does. So EDGs make positives more stable, EWGs make negatives more stable. And the stronger you are, the more of an effect you will have. So right off the bat, we can say, okay, we have a withdrawing group with a positive, that's no good. 1 is definitely the least stable. But now comparing 2 to 3, what's the difference? Because they both have a strong withdrawing group. What changes about it? Let's look at how that, I said withdrawing group. Both 2 and 3 have strong donating groups, but so what's the difference? What you have to do is you have to consider the resonance of that positive charge from this point forward. So if I look at this oxygen for number 2, that oxygen can resonate down, and this double bond can resonate over to the positive charge. And so this has a nice resonance structure where you get the positive on the oxygen, which is good. Between carbon positive and oxygen positive is the better deal because you still have a full octet due to the lone pairs. Yes, oxygen is more electronegative, so you'd think, okay, it doesn't like being positive as much, but the octet rule wins over everything. If you still have a full octet, that makes you a better contributor to the resonance. And so now I have a double bond over there. And so this would be the resonance structure, nice and stable. Now let's try and have this oxygen resonate with that positive. Can it actually do that? If this oxygen tries to swing down, put its electrons in, can anything resonate over to this positive? It can't, because the only way that this double bond could form is if a bond on this carbon breaks, right? That's what we did here. When this swung down, this double bond had to move out of the way to allow that to happen, which means the only way this oxygen can ever resonate down is by moving that double bond over there, which means this oxygen will never get to see this positive charge. And for that reason, 3 is less stable than 2. It's better than 1 because it still has a donating group rather than a withdrawing group, but because it can't resonate with that positive, because you can't actually get the positive on the oxygen, this one is much better. And so the answer to this question was choice